So it's a pleasure to be here, if only virtually. So I'm going to talk about joint work with Daniel Alpay and Ariel Pinchas. And let me start by reminding, even though it's probably not necessary for most people in this audience, but still to put some dot over the i's, the classical Beurling theorem. So we consider the Hardy space of the unit disk, which consists of all analytic functions on the unit disk, analytic, such that the supremum of the integrals over the circumferences is bounded, and the integral here is over the unit circle. And this is a Hilbert space, of course. And the inner product is just the limit. And every f in the Hardy space has non-tangential boundary values. Almost everywhere on the circle, and in fact H2D is the subspace of the L2 space on the boundary, and it's just the analytic subspace. In the sense that L2 decomposes into orthogonal direct sum of H2 and the H2 of the complement. And here, when we talk about the H2 of the complement, we have to take the functions which vanish at infinity. And it's kind of in relation what will come up next when we talk about the Riemann surface case. It's really because, so this means vanishing at infinity. And the point is that, as will become apparent in the Riemann surface case, the elements of this space are really not functions, but they are what's half-order differential, so therefore form f times square root of dz. So if you want, on the disk, of course, it doesn't matter, but when you go to infinity, z has a first-order pole, dz has a second-order pole, square root of dz has a first-order pole. So if we want this to be analytic, then f has to vanish. And then another item is that, of course, is also well known, is that H2 is a reproducing kernel Hilbert space. With reproducing kernel, which is basically the version of the Sega kernel. So it's 1 over 2 pi, 1 over 1 minus ZW bar. And that means that K, for any W, this belongs to the space, and that the scalar product reproduces the value of the function. Okay, so that's the Hardy space. And on the Hardy space, there is, of course, the natural isometry. So there is mz, which sends f to z times f, multiplication of the independent variable, and Beurling's theorem, which is kind of one of the cornerstones of at the interface between complex analysis and operator theory, describes all closed invariant subspaces of this isometry. So Beurling's theorem tells us that M is a closed invariant subspace of MZ if and only if there exists a unique up to a constant unimodular factor inner function S on D such that M is just S times H2, and here an inner function means just that S is analytic, contractive. So S of Z less or equal than 1 for all Z. Since it's contractive, it has boundary values almost everywhere on the unit circle, and the boundary values are almost everywhere equal to 1. Okay, so that's Beurling theorem, and that is closely related to operator model theory. Namely, if we have S, and if we now take T to be, so SH2 is invariant under multiplication by Z. Now we take this orthogonal complement and we compress multiplication by Z there, so we get now a contraction. And if we look at this contraction, so this is going to be a completely non-unitary contraction. And furthermore, it's a model. So any completely non-unitary contraction with defects 1, 1 and of class C0, 0 is of this form, so is unitarily equivalent to such an operator T for a uniquely determined, again, up to a constant unimodular factor, inner, let me say here, scalar valued inner function S, and S is called the characteristic function of the completely non-unitary contraction T. And it can be calculated explicitly from T. So I'm not going to define what are defects 1, 1 and what is class C 0, 0. It's related to the fact that the characteristic function that we get here is scalar valued and inner. So if the defects were not 1, 1, then we'd get a matrix operator valued function. And if it were the contraction is not of class 0, C 0, 0, we'll get a contractive function which is not inner. And in both cases, there are versions of Beurling's theorem. In the matrix valued or operator valued case, it's the Lax-Helmholtz theorem, which generalizes Beurling's theorem to the case when we consider vector valued Hardy space, so Hardy space whose elements are vector valued rather than scalar valued functions. And in the case of contractive functions which are not inner, this is the work of the branch on contractively included subspace rather than isometrically included subspace of H2, which are invariant. And well, this is, of course, is the beginning of the operator model theory. So that's the work of Matt Foyash in the 60s, but it really goes back to the work of Lifshitz in the 40s, 50s, and it's closely related to the work of the Branch and Rovniak. And many subsequent ramifications. Now, what I want to emphasize at this point is that, in fact, one can use this relation with operator theory, with operator model theory, to prove Beurling's theorem. Namely, if we are given a subspace of H2, which is invariant under multiplication by Z, we can kind of play the same game. We can take the orthogonal complement, the coinvariant subspace, we can compress multiplication by Z to this coinvariant subspace, we'll get a contraction. And if we take the characteristic function of this contraction, we get a completely non-unitary contraction, which actually will have defects 1, 1, and will be of class C 0, 0. And if we take its characteristic function, it exactly will be we'll get exactly the Beurling representation S times H2 for the original invariant subspace. And in fact, this kind of approach to invariant subspace theorems have been explored a lot by Jobal, a lot of it in joint work with Volodya Bolotnikov in various more general situations, both commutative and non-commutative. Okay, so these were a few reminders about the classical case, and now I'm interested in generalizations to Riemann surfaces or to multiply connected domains. So let S be a finite bordered Riemann surface. Some genus, and L with K boundary components that I'm going to denote x0, x1 through xk minus 1. And if you don't like Riemann surfaces, you can just take a multiply connected planar domain of finite connectivity, finitely connected planar domain, So in this case, L is 0, but there are several boundary components. And if you want to be even more concrete, you can take an annex. So that's the simplest case beyond the unit disk. So L will be 0 and K will be 2. So there will be 2 boundary components, the inner circle, the outer circle. And the theory is already interesting in the case of the annex. Okay, now we are going to consider Hardy spaces on this finite bordered Riemann surface or finitely connected planar domains. And a key feature which became apparent in the work of Widom and others back in the 60s is that you really have to consider, since your domain is now multiply connected, you need to consider multi-valued functions. Just considering functions is not enough. It will be clear when I will get to Beurling's theorem in a minute. So we let alpha be a unitary character on the fundamental group. And notice that we are really talking that 2L plus K minus 1 numbers of absolute value 1. 2L numbers for the genus, for the handles, which are on the inside of the domain, if there are any, and then K minus 1 numbers for going around every boundary component. And we are going to consider H2 of S. I'm going to write here alpha tensor delta, Hardy space of sections of alpha tensor delta. So basically, these are multi-valued functions that pick up a multiplier, which is given by alpha when we go around a closed loop on our multiply connected domain. Now there is this delta, and that's a technical point. So delta is what is called a line bundle of half-order differentials. And of order, and what it means is that if we have 2 coordinate charts, so in terms of the coordinate charts on our Riemann surface, on UI intersection UJ, so in terms of the coordinate charts, our half-order differential is given by Fi of Zi square root of dZi, and on the intersection we have Fj of Zj equals Fi of Zi times square root of dZi over dZj, where we have to be a little bit careful to choose the values of the square root so that the cocycle relation is satisfied. So the technical point here is that, of course, if we're on the planar domain, we can just integrate with respect to the arc length. More generally, we can integrate with respect to a representing measure. But since it's more natural, since we are on the Riemann surface, it's more natural to integrate differentials rather than functions. So the point here is that if Fg are holomorphic sections of alpha tensor delta on S, then for a path C, the integral over C of F G bar is well defined. So this is somehow a natural canonical object to look at rather than to look at functions. Okay, but the crucial thing is the multivalues. Okay, so now we have, and there is a version of Beurling's theorem here. So Beurling's theorem for S. So M, which is a subspace of the Hardy space of multiplicative half-order differentials, is closed and invariant under multiplication by y. Now we have to be, there is a little bit of a freedom here, but let's say it's invariant under multiplication by y for all y analytic on S and continues on S union the boundary of S, if and only if M is of the form S times H2, and there is another character here, alpha. So so that's the reason we need multivaluedness, because even if alpha tilde was trivial, and forget about half-order differentials, we'll get some alpha. So there is a shift in multivaluedness between the output and the input, so to say. So if and only if M is S times H2 for, again, a uniquely determined character alpha on pi 1 of S, and a uniquely determined, again, up to a constant unimodular factor. And S will have multipliers, so we have multipliers alpha tilde in M at the input side, so to say, we have multipliers alpha, so S will have to have multipliers alpha tilde times alpha input. So inner section S of alpha tilde alpha inverse. So S is, and notice that the multipliers have absolute value 1, so the absolute value of S is well defined. So S is contractive, the non-tangential boundary value is almost everywhere of absolute value 1, and its multipliers are alpha tilde alpha. And essentially, this theorem is due to Wojcik. In the 1960s, and there have been earlier results. Saracen, in the case of the annulus, there are related results of Hasumi, also in the case of infinite connectivity, of Forelli. And this is a scalar valued case. There is a vector valued case, so the analog of Lex-Helmholtz theorem. Which is the work of Abraham C. Douglas and Ball. And there is also a related work, later work in the 90s of Pavlov and Fedorov. And we have an alternative proof, which is related also to what I'm going to talk about, which is related to operator model. Okay, so let me now move towards what I kind of promised in my title in my abstract. So for an indefinite version of Beurling or Beurling-Helmholtz theorem. So for this, first of all, notice that there is, okay, so we consider this H2 spaces on S just by integrating, well, I didn't write the definition, but the definition is obvious. We just integrate over each boundary component, or kind of go a little bit inside, take the integral, and then let those inner contours approximate the boundary components. But given the fact that now we have more than one boundary component, we can assign signs to those boundary components, and that will give us some indefinite inner product. So there is a natural indefinite inner product on H2 spaces on S. Namely, we pick up signs nu I, or signs, so let me say -1 to the power nu I, where nu I is either 0 or 1 for all boundary components. And let's say by convention that nu 0 is 0, so give plus sign to the component at 0. And let the indefinite scalar product of f and g be the summation over all of the boundary components, and we integrate over every boundary component. So here I'm already taking non-tangential boundary values, but we can also do the approximation from the inside. But the point is that when we take fg bar, and again, technically remember that fg bar can be integrated on any path, it's well defined, we don't have to choose a measure, but the crucial thing is that now we assign signs. Okay, so we get an indefinite inner product, and now, okay, so we get an indefinite inner product space. Now, if we want to deal with indefinite inner product spaces, then in finite dimension, we can just require, in order to have a reasonable behavior, that the inner product is non-degenerate. So there are no vectors which are orthogonal to the whole space. In the infinite dimensional setting, this is not enough. And so in general, what we need is to consider what is called a Krein space. So K, our indefinite inner product space, splits into orthogonal direct sum, but since we have an indefinite inner product, I'll put those square brackets of K plus and K minus, where K plus is a Hilbert space and K minus is an anti-Hilbert space. So those are Hilbert spaces. And such a decomposition is not unique, but any two decompositions are naturally can be transformed one into the other. And there is a natural topology coming from the product topology on k plus and k minus. And there is a meaningful grain space operator theory. Again, this is quite a classical I-water topic with many applications. And in particular, there is an indefinite version of Beurling's theorem due to Ball and Halton, which they then have applied very successfully to many classical interpolation problems, and which is well, what I'm kind of getting at is a generalization of that to this multiply connected set. Okay. Okay, so we have this natural indefinite scalar product on our Hardy space on a multiply connected domain. So the two questions are, is it indeed a Krein space? So one is this H2, this signs nu Krein space. Is it even non-degenerate? That's not obvious. And I should say that that's an unusual situation, because usually in a situation where Krein spaces arise in practice, in most cases, you kind of see obviously that it's a Krein space. The fundamental decomposition, the decomposition to k plus and k minus sort of screams at you. Here, that's not the case. It's not clear. And two, of course, if yes, is there a Beurling type theorem for invariant subspaces subspaces of this space. Okay, so to give the answer to the first question, I have to introduce a little bit function theory on our S. And the crucial construction, which is very classical, goes back to the work, if not of Riemann, then of Schottky, is the notion of the double. So S is a Riemann surface with boundary, or a multiply connected domain, and we take a copy of it and glue to it along the boundary to get a compact Riemann surface. So for instance, if you started with an annulus, you glue to it another annulus along the boundary, you get a torus. So let X be the double of S. So X is a compact Riemann surface. Of genus G, which is 2L plus K minus 1. And it comes equipped with an anti-holomorphic involution. Anti-holomorphic involution, which interchanges S and the copy of S that we glued along the boundary. Let's call it tau. And X decomposes as X plus union XR. The meaning of R will become clear in a second. And X minus, where X plus is S, tau interchanges X plus and X minus, and XR, which is the boundary of S, is fixed by tau. Now, the reason for the notation R and writing X sub R is that from the point of view of algebraic geometry, X is what is called a real Riemann surface. So, and since it's compact, it's really a Riemann surface, a desingularized Riemann surface of a real algebraic curve which is given by real equations, and the real points on the curve are exactly the boundary. Okay, now getting back to the answer that I would want to give to question 1, we pick up. Maybe let me start a new screen here. So pick up a canonical homology basis on the double, which is symmetric in a certain sense under the anti-homomorphic involution, whatever it means, and a corresponding normalized basis of holomorphic differentials, so abelian differentials of the first kind, omega 1 through omega g, and those differentials would be actually invariant under tau or real. That follows from the fact that we choose our homology basis to be symmetric. And then, as on any compact Riemann surface, we have the so-called Jacobian variety. Which is a G-dimensional complex torus. It's CG modulo the so-called period lattice, which is the lattice formed by integrating the differentials over all closed paths, or all one cycles on our Riemann surface. And the point is that this G-dimensional complex torus has a natural complex conjugation on it because lambda is invariant under this period lattice, is invariant under complex conjugation because of the symmetry choices that we made. And again, as for any compact Riemann surface, there is the so-called Abel-Jacobi map, which embeds our X into the Jacobian variety. So it sends a P to, we just integrate our differentials over some path from P0 to P, where the base point P is convenient to choose it here on X0. That's not well defined because it depends on choice of path, but it's well defined in the quotient in the complex form. So this is sort of the fundamentals of the function theory on the double, which is a compact real Riemann surface. Now, what that has got to do with our Hardy spaces and our indefinite Hardy spaces? So the point is that that takes some calculation. So what do we want to do? We want to extend, and I should say that the reason for working on the double is because we have all the powerful tools of the classical theory of compact Riemann surfaces. So that's why it's so natural to work on the double, and that, of course, is an old idea which goes back to Schottky, was extorted out by alphas and many other things. So we want to extend our alpha, or alpha tensor delta, our multiplicative half-order differentials, which is defined, the bundle of multiplicative half-order differentials, which is defined on S, on X plus. So to a line bundle on the double. So again, to a line bundle basically of multiplicative half-order differentials. So the multiplicative is now going to be parameterized by a point in the Jacobian variety on this complex torus. But we want this extension to be symmetric. So, and the right kind of symmetry, as it turned out, is that this extended bundle, when we basically multiply it, when tensor it with the conjugate, we get the canonical bundle, the bundle of differentials on our Riemann surface. And again, the point is that we want to be able to integrate products over closed paths. And that, when one does the calculation, means simply that this point zeta, that in the Jacobian variety, has to be purely imaginary. And now such purely imaginary points can be all parameterized. So the set of all points zeta in the Jacobian variety, such that zeta plus zeta bar equals 0, is a disjoint union of real tori. So tin U is a G-dimensional real torus, where nu are like those signs that we had before. So nu is nu 0, nu k minus 1, which are 0 or 1s. And let me say nu 1 through nu k minus 1, nu 0, and normalize it to be 1. And then the point is that, remember, the character alpha depended on G real numbers. We want to lift it to this G-dimensional complex torus, but not anywhere on this union of the nu. So the bottom line is that for each alpha unitary character on our finite bordered Riemann surface S, and each choice of signs nu, there exists a unique zeta in tin u in each one of these tori, such that if we take out zeta and restrict it to S or to X plus, we obtain. And what this has got to do with our harvest classes. So for instance, it's a relatively easy exercise to see, I mean, H2, the usual H2, the Hilbert space H2 on S, of course, it's a reproducing kernel Hilbert space, that's easy to see, but one can write an explicit formula for the reproducing kernel using all this machinery. So H2 of S with values in alpha tensor delta is a reproducing kernel Hilbert space with reproducing kernel K zeta 0 PQ, which is, well, 1 over 2 pi I. And then there is certain expression involving theta functions associated to this Jacobian variety. E of P tau Q. where theta is a theta function and the E is the so-called prime form. So again, these are basic and well-known objects in the classical theory of compact Riemann surfaces. And the point is that there is a denominator here. So E of P tau Q is like P minus tau Q, or 1 minus, it's like the Sega kernel. Of course, it's more complicated here because multi-valuedness, etc. So, but there is this theta of zeta 0 of 0, which is essentially the same as theta of zeta 0. So what I take here is the lifting of alpha to the torus T0. And that gives me the reproducing kernel for the Hilbert space when there are no signs. And this thing is always not zero. And it turns out that that gives the answer to question 1. So fairly old result of Danielle and myself is that H2 nu is non-degenerate if and only if theta of zeta nu is not 0. The point is, again, theta of zeta 0 will be always not 0. Theta of zeta nu usually will be not 0 generically just because of analyticity, but sometimes it could be 0. So it's non-degenerate if and only if this is not 0. And then it is a crime space. And in fact, it's the analytic subspace of L2. So L2 nu of the boundary will be H2 nu on X plus of L zeta nu tensor delta orthogonal direct sum with respect to indefinite inner product H2 nu X minus L zeta nu. So this function theory on the double gives us exactly the answer of when it's non-degenerate in the Crane space, and then we also have the usual decomposition of L2 and H2 plus and H2 minus. And in the few minutes that I have left, let me formulate Beurling's theorem, our result. So indefinite Beurling theorem on S. So let M be a subspace of H2 nu for some alpha tilde, and I assume that the condition that we had before is satisfied, so that it's non-degenerate in the Crane space, and let it be closed subspace invariant again under multiplication by functions, analytic on S, and continuous on S union ds. And now in the Crane space setting, you have to be careful because a subspace of a Crane space, a closed subspace, is not necessarily a Crane subspace. A subspace can be degenerate or not orthocomplemented. So assume that its orthogonal complement is ortho-complemented. And then there are some extra technical assumptions that I don't want to get into, and that probably can be eventually removed. They're kind of the artifact of the limitations of our technology. Then there exists a unique alpha character on S. Again, it satisfies the non-degeneracy condition theta of zeta nu is not zero, the non-degeneracy condition with the same u, and a unique up to unique unimodular factor meromorphic section S of alpha tilde alpha inverse on S with non-tangentially boundary values almost every equals 1. Such that M equals S H2 nu of alpha tensor delta. So that's a version, an indefinite version of Beurling's theorem. I spoke here only about the scalar valued case. There is also a vector valued case when you consider vector bundles rather than, so your multipliers are now have values in unitary matrices rather than complex numbers with absolute value 1. It's quite, the results are quite analogous, but there are no beautiful closed formulas for reproducing kernels in terms of theta functions because kind of matrix value theta functions are still not well understood. And I'm afraid I'm already out of time. So let me just say I didn't have time to talk about the operator model theory, which is associated to it. So the operator model theory is associated now to a pair of operators. So the point is that now, if you have such an invariant subspace, indefinite or in indefinite setting, you can take its orthogonal complement, H2 minus SH2, and then you can take a pair of meromorphic functions, y1 and y2 on your Riemann surface, and you take operators of multiplication by them, and you can compress them to this coinvariant subspace, and that gives you models for pairs of, I'm here kind of in upper half plane rather than unity setting, so not contractions, but commuting non-self-adjoint operators with finite non-Hermitian ranks, and that's a theory which are always related to an algebraic curve. There is a certain discriminant curve associated with such pair of operators, and that's a theory which was originated by Lifshitz in the 80s. And let me stop here. Thank you very much.
Right, thank you. I was going to ask whether there are any explicit formula for the theta functions, but I believe you said that they were not.
You mean in the matrix valued case?
Yes.
Yeah, so, well, in genus 1, you can write it down because the fundamental group is abelian. So basically it will be, you know, like when you have a Jordan cell. So it will be like theta functions and derivatives, basically of theta function. In general, I think, well, of course, it depends on what you call explicit. You can say, you can look at the modular space of stable bundles, and you can consider there the corresponding generalized theta divisor, and you can take it's going to be ample. You can take it sufficient. You can take sections of its sufficiently high tensor power, and okay, that will be an analog of theta function. But if you want for something more explicit, I think that's a rather open question. There has been a very interesting work by Fay in the early 90s, which maybe comes close to that, but I don't think anything beyond.
Right, thank you. Well, I'd like to therefore thank Victor Vinnikov for giving a clear presentation of an interesting classical topic that's still under evolution.